All right, let's jump right into this explainer for St. Paul American School Clark, grade 9. Today we're diving into geometry, specifically Unit 2, Lesson 6, Compose transformations and describe their effects. If you've been practicing your basic reflections, translations, and rotations, well, you are completely ready for the next level. We're going to unpack exactly how you can stack these rigid transformations together, and more importantly, how to easily calculate their final effects.
Here's our game plan for today. We'll start with our lesson objective, run through an explanation of compositions, tackle a worked example together, do a quick misconception check to avoid common traps, pause for a formative check, and finally, wrap it all up with a concept recap. Let's get to it.
Section 1, Lesson Objective.
So the absolute main goal of this lesson is learning how to perform compositions of rigid transformations. By the end of this, you're going to know how to execute glide reflections, and you'll be able to quickly determine the effects of reflecting a shape over parallel lines as well as over intersecting lines. It's really cool stuff. Section 2, Explanation of Compositions. Okay, so what exactly is a composition of transformations? Well, when you perform a composition, you're basically just taking a single shape and applying multiple rigid changes to it, like doing a reflection and then immediately following it up with a translation. But here's the key. You are perfectly maintaining the original shape's size and angles. Because each individual step is a rigid transformation, the final result is what we call an isometry. That just means the shape literally doesn't stretch, it doesn't shrink, it doesn't distort at all. It simply lands in a brand new position or orientation. Now, let's look at a really specific, really common type of composition called a glide reflection. Honestly, the best way to think about a glide reflection is to just picture footprints in the sand. When you take a step, you basically mirror your left foot over a central imaginary line to become your right foot, right? And then you translate it forward, parallel to your path of walking. So a single everyday footstep is actually a perfect real-world example of a glide reflection. Beyond glide reflections, we have two major shortcut rules for composing two reflections, and you definitely want to memorize these. First up, when you reflect a shape over two parallel lines that are, let's say, h units apart, the visual result is exactly the same as if you just did a single translation of 2 times h units. You just double the distance. Second, if you reflect over two intersecting lines that meet at an angle of x degrees, the final image is equivalent to a single rotation of 2 times x degrees. These theorems are absolute game changers because they save you so much time. Section 3, Worked Example. Let's actually look at the coordinate plane to see how this builds a complete picture. We're going to perform a glide reflection on a triangle, but to keep it simple, let's just trace a single vertex, point A. First, point A starts up at 8, 8. We flip it across the y-axis, which lands it at A prime, negative 8, 8. Simple enough, right? Then, we translate that new point 8 units straight down, leaving us at A double prime, negative 8, 0. But here is where it gets really interesting. We don't actually have to do this whole thing in two separate clunky steps. We can mathematically describe the entire composition with just one elegant algebraic rule. We literally just take our original coordinates, x and y, and apply the changes simultaneously. So the rule becomes x, y maps directly to negative x, y minus 8. Boom. That one single formula accomplishes both the reflection and the translation instantly. Section 4, Misconception Check. Before we go any further, I want to point out a few traps that students frequently fall into when mapping these compositions. First, people often confuse horizontal and vertical shifts. Just remember, horizon literally sounds like horizontal. That's your flat x-axis. Another huge common error is accidentally sliding a shape when you're actually supposed to reflect it. To fix this, visualize literally folding your graph paper along that axis of reflection. And finally, for rotations, students often mistakenly pivot the shape around one of its own corners. No, you've got to always anchor your movement to the true center point. So map those coordinates carefully. Section 5, Formative Check. All right, let's test this out. Two parallel lines are exactly 7 units apart. If you reflect a figure over both of those lines sequentially, how far apart will the starting image and the final end image be? I want you to visualize this double reflection in your head right now and apply that specific shortcut theorem we talked about a minute ago. Think about the relationship between the distance between the lines and the total distance the shape moves. Did you get 14? Because if you did, you are absolutely correct. Remember, the reflections over parallel lines theorem tells us the total translation is exactly 2h. So 2 times that 7-unit distance means your final image is exactly 14 units away from where it started. See? It's a fantastic shortcut. Section 6, Concept Recap.
Okay, let's bring this all together. The most crucial takeaways today is that complex transformations can actually be simplified into single, easy-to-use rules. Whether that's doubling the distance between parallel lines to find your translation, or doubling the angle of intersecting lines to find your rotation. We also learned that composing multiple rigid transformations always yields an isometry. That means your true shape and size remain perfectly preserved no matter how many times you flip, slide, or spin it around the graph. So I want to leave you with this final thought. If a single glide reflection perfectly maps one human footstep, what exact mathematical composition rule would you need to program a robot to autonomously navigate a complex, winding hallway? Think about it. These strict geometric rules of composition don't just live on your graph paper. They are the absolute foundation for coding real-world movement. Every single time your GPS reroutes your car, or a video game character moves through a 3D world, software is rapidly calculating these exact same compositions of transformations. Geometry is everywhere. You just have to know how to look for it.